This video is going to cover section 3.2 on independent and mutually exclusive events. First thing to note that independent and mutually exclusive do not mean the same thing. So two events, A and B, are independent if the knowledge that one occurred does not affect the chance the other occurred. So for example, the outcome of two rolls of a fair die are independent events. The outcome of the first roll does not change the probability for the outcome of the second roll. Two events are independent if the probability of A given B already occurred equals the probability of A. We don't care that B already occurred. Similarly, that the probability of B given A equals the probability of B. It doesn't matter that A already occurred. And the probability of A and B is equal to the probability of A times the probability of B. So if two events are not independent, we say they are dependent. And if it's not known whether A and B are independent or dependent, we assume they are dependent until we can show otherwise. So we've talked about sampling before, and so sampling can be done with replacement or without replacement. So with replacement means that if each member of a population is replaced after it's picked, then that member has the possibility of being chosen more than once. So events are independent. The result of the first pick does not change the probabilities for the second pick. Now, without replacement, each member of a population may be chosen only once. The probabilities for the second pick are affected by the result of the first pick. The events are dependent or not independent. So hopefully that makes sense. That put it back, that's with replacement, and so what you do the second time, isn't changed because of what happened the first time. But if you don't put it back without replacement, then your options have changed for the second pick. So an example, you have a fair, well-shuffled deck of 52 cards. It consists of 4 suits. The suits are clubs, diamonds, hearts, and spades. S for spades, H for hearts, D for diamonds, C for clubs. And there are 13 cards in each suit consisting of A, which is the ace, 1, which is the ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, J for the jack, Q for the queen, and K for the king of that suit. And 3 cards are picked at random. So if we know that the picked cards are the queen of spades, the king of hearts, and the queen of spades, can we tell if the sampling was done with or without replacement? Well, with replacement, because the queen of spades was picked twice, and it only exists once in the deck of cards, and so we must have placed it back in, so we must have replaced it to be able to pick it again. Suppose we know that the picked cards are the queen of spades, the king of hearts, and the jack of spades. Can we tell if the sampling was done with or without replacement? And in this case, we can't tell. Maybe we put the queen of spades back in and we just didn't pick it. Same thing with the king of hearts. So this one, you can't tell if it was done with or without replacement. Another example, we're going to draw 2 cards from a standard 52 card deck with replacement. What's the probability of getting at least 1 card? So if we're talking about just the color for the cards when we're picking the cards, so the sample space for drawing 2 cards with replacement from a standard 52 card deck with respect to color is you could pick a black card and then a black card, a black card and then a red card then a black card, or a red card and then a red card. So that's why I wrote out the sample space so we could see what the options were. So event A is getting at least 1 black card, and that consists of black, 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 red, or red, black. So the probability of event A is 3 over 4. So the outcomes we want divided by the total outcomes. So 3 over 4 or 0.75. So now mutually exclusive events are events that cannot occur at the same time. This means A and B do not share any outcomes and the probability of A and B equals 0. So suppose we have the sample space S equals the numbers 1 through 10. We're going to let event A be the numbers 1 through 5, event B be the numbers 4 through 8, and event C be the numbers 7 and 9. Then A and B are the numbers 4 and 5, and the probability of A and B is 2 out of 10. So again, the two outcomes we want divided by the 10 total outcomes in our sample space. This is not equal to 0, so therefore A and B are not mutually exclusive. I mean, sometimes you can tell without figuring out the and probability, but that's just one way to do it if you need to. Now, A and C do not have any numbers in common, so the probability of A and C is 0. Therefore, A and C are mutually exclusive. If it's not known whether A and B are mutually exclusive, you have to assume they are not until you can show otherwise. So a box has two balls, one white and one red. If we pick one ball and put it back in the box and then pick a second ball, so that's sampling with replacement, we're going to find the probability of the following events. Let's let event F be the event of getting the white ball twice, so white, white. G is the event of getting two balls of different colors, so that would be white, red, and red, white. H is the event of getting white on the first pick, so that would be white, red, or white, white. And then questions, are F and G mutually exclusive? And are G and H mutually exclusive? So again, our sample space here is white, red, white, white, red, white, and red, red. The event F, like we said, is the event getting the white ball twice, so it's just white, white, and that is 1 out of 4. G is two balls of different colors, so red, white, or white, red, and the probability of that would be 2 over 4, which reduces to 1/2. And then H, the event of getting white on the first pick, white, red, white, white, again, 2 over 4, which reduces to 1/2. So are F and G mutually exclusive? If we look at them, we want to figure out if they have anything in common. So again, you can look at the events listed out there, the outcomes in the events, to see if there's anything that they share and figure it out. So this is white, white, white. White does not happen in G, so they are mutually exclusive. And then for F and H, white, white does occur in H, so F and H are not mutually exclusive. So you can see from the previous example that we can figure out the and probability, and if it's 0, they're mutually exclusive. If it's not 0, they're not mutually exclusive. Or you can just look at the outcomes in the respective events to figure it out. Another example, a student goes to the library. We're going to let events B equal the student checks out a book and D equal the student checks out a DVD. So this time we're given probabilities. So the probability that the student checks out a book, the probability of event B is 0.4. The probability that the student checks out a DVD is 0.3. And the probability that the student checks out a book and a DVD is 0.2. So we're going to find the probability of B given D. So that's picks out a book given they've already picked out a DVD. We're going to do it the other way, the probability that they pick out a DVD given they already picked out a book. And we're going to say, are they independent, the two events, and are they mutually exclusive? So remember our formula for our conditional is going to be the probability of B and D divided by the probability of D. We're given those numbers, so it's 0.2 divided by 0.3, which reduces to 2/3 or 0.67. The conditional D given B, so again, same thing on top, the probability of B and D, but now divided by the probability of B. So that's going to be 0.2 divided by 0.4, which is 1/2 or 0.5. And what we can say is that B and D are not independent, because if they were, the probability of B given D would have to equal the probability of B. And we can see that 0.67 does not equal 0.4. The probability of D given B, which was 0.5, does not equal the probability of D, which was 0.3. And the probability of B and D does not equal the probability of B times the probability of D. The probability of B and D was 0.2. And if you multiply the other two together, 0.4 times 0.3, it's not 0.2. So the last question, are B and D mutually exclusive? So I want to know if the and is equal to 0 or not. It is not equal to 0, so they are not mutually exclusive. So I put this example in because it's another way sometimes that we get probabilities or problems. So this one in a basketball arena, 70% of the fans are rooting for the home team. 25% of the fans are wearing blue. 20% of the fans are wearing blue and are rooting for the away team. And of the fans rooting for the away team, 67% are wearing blue. So first of all, those are listed, they're given to us in percents, and so we have to think about them as decimals or fractions if you wanted to. And then here, when it says and rooting for the away team, up here we know the home team, who's rooting for the home team. The away team, who's rooting for the away team, would be the complement of that. So we actually know what that probability is as well. And then this last one here, this is a conditional. Of the fans rooting for the away team, 67% are wearing blue. So that's blue given rooting for away. So let's let A be the event that a fan is rooting for the away team. Let B be the event that a fan is wearing blue. Are the events of rooting for the away team and wearing blue independent, and are they mutually exclusive? So first off, the probability of A, so that's rooting for the away team, is 0.3 because it's the complement of rooting for the home team. The probability of B, that the fan is wearing blue, they gave that to us, so it's 0.25. And then the probability of the probability of A and B, so that you're rooting for the away team and wearing blue, is 0.2. So that was also given to us here. 20% is 0.2. So now we need to figure out the conditionals, and we need to figure out, well, we can say right now the mutually exclusive answer, right? Because away team and blue is not 0, so they are not mutually exclusive. But jumping ahead. So probability of A times the probability of B, 0.3 times 0.25 equals 0.075. That is not equal to 0.2. The probability of A given B, so that's going to be the and 0.2 divided by the probability of B, 0.25, that reduces to 0.8. That is not equal to the probability of A, which is 0.3. And the probability of B given A, 0.2 divided by 0.3, is 0.67, and that is not equal to the probability of B. So what we know is that the events rooting for the away team and wearing blue are not independent, and they are not mutually exclusive. Sometimes working through those examples and those problems can be tricky, so I would definitely recommend you write down and write out everything you know, the events, what's in the sample space, like in those other problems. This one we don't have a sample space, but we have the probabilities, everything you need to know, and do out the math so it's in front of you and you're not just trying to do it in your head. So I have a few more examples for these problems. If you feel like you get everything now, you can sign off. This was section 3.2 on independent and mutually exclusive events. But if you'd like to stick around, I'm going to go through a few more examples of this stuff. So try it 3.13 in our book. A box has 2 balls, one white and one red. We select one ball, we put it back in the box, and then we select a second ball. So this is sampling with replacement. So we know it's independent. We're going to let T be the event of getting the white ball twice, F the event of picking the white ball first, and S the event of picking the white ball in the second drawing. So this is one of those times where I think it's a really good idea to write out what's in your sample space and then what's in each event, the outcomes in each event. So eventually we're going to compute the probability of T, the probability of T given F. We're going to answer the question, are T and F independent? Are F and S mutually exclusive? And are F and S independent? So our sample space, white, 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 red, red, white, red, red. So those are listed here. Our event T is getting the white ball twice, so it's white, white. F is the event picking the white ball first, so white, white, or white, red. And S is picking white in the second drawing. So that could be white, white, or red, white. So our probability for the event T, there's one outcome that we want, one favorable outcome over our sample space, so 1/4. The probability of picking the white ball first, so the probability of event F, so there's 2 favorable outcomes in F divided by 4, so that's 1/2. And the same thing for the probability of picking the white ball in the second drawing, 2 out of 4 or 1/2. So the probability of T and F, so picking the white ball twice and picking the white ball first, is going to be just 1, right? So all they share in common is white, white. If we look at T and we look at F, the only one they share is 1, so 1 out of 4. So our conditional, picking the white ball twice, given we picked the white ball first, is 1/4 over 2/4, okay? And if we do the math, remember, when you divide by a fraction, you flip it and you multiply by the reciprocal. So this ends up reducing to 1/2. The probability of F and S, so if we look at F and S, we have white, 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 red, white, white, red, white. So we, again, only share white, white. So we have 1/4. And that makes our conditional F given S, so picking the white ball first, given we picked the white ball in the second drawing, is going to be the and, so 1/4 divided by the probability of F, which was 2/4, and I kept those same denominators so that when I did the flip, they canceled, and that reduces also to 1/2. So T and F are not independent because this one, T given F, does not equal the probability of T, and this one, the probability of F given S, does not equal the probability of F. Actually, they are independent. Like, they do equal that. I jumped ahead. I was thinking that it was, forgive me. So T and F are not independent. This one here does not equal T, which was 1/4. This one does equal F, so they are independent. And then the mutually exclusive, F and S are not mutually exclusive because the and is not 0. So hopefully that made sense. So our try at 3.5, this is a replacement question. You have a fair, well-shuffled deck of 52 cards. It consists of 4 suits. The suits are clubs, diamonds, hearts, and spades. There are 13 cards in each suit. And suppose that you sample 4 cards without replacement. Which of the following outcomes are possible? So we're picking a card and we're not putting it back in. So can we get the Queen of Spades, the Ace of Diamonds, the Ace of Clubs, and the Queen of Diamonds? It's possible because none of those repeat. So that could be what we get. Can we get the King of Hearts, the 7 of Diamonds, the 6 of Diamonds, and the King of Hearts? No, because we can't pick the King of Hearts twice if we don't replace it. And then the Queen of Spades, the 7 of Diamonds, the 6 of Diamonds, and the King of Spades. Is that possible without replacement? It is. So try at 3.9. In a bag, there are 6 red marbles and 4 green marbles. The red marbles are marked with the numbers 1, 2, 3, 4, 5, and 6. The green marbles are marked with the numbers 1, 2, 3, and 4. So R represents a red marble, G a green marble, O an odd numbered marble. So the sample space for picking one marble is a red 1, a red 2, a red 3, a red 4, a red 5, a red 6. Right, because there were 6 red marbles marked with the numbers 1 through 6. And then the 4 green marbles are green 1, green 2, green 3, and green 4. So we have 10 outcomes in this sample space. So what is the probability of G and O? What is the probability of getting a green marble and an odd number marble? And then are G and O mutually exclusive? So if the and is equal to 0, they're mutually exclusive. If it's not equal to 0, they are not mutually exclusive. So the probability of picking G, green, and odd is going to be G1 and G3. So that's going to be 2 over 10, or 1/5, or 0.2. So they are not mutually exclusive. So that was the additional examples for section 3.2, which was on mutually exclusive and independent events.